Hey everyone! Welcome back to Education is Life, your go-to channel for unlocking the wonders of learning. It is me, Joe Edgo, and today we're on Lesson 11 of the Arduino UNO R4 Ultimate Training Series, focusing on servo motors and building a single-axis solar tracker using photoresistors. For today's lesson, you'll learn how to control a servo motor using two different servo libraries. Then you'll learn how to position a servo motor using a potentiometer and a photoresistor. At the end of this lesson, you'll create a simple solar tracker using two photoresistors, simulating east and west locations, and a servo motor to position the solar panel. As always, before we start, I'd like to extend my sincere gratitude to SunFounder for sponsoring this course and enabling everyone, especially beginners, to embark on this comprehensive educational adventure. Throughout this series, I'll be using this amazing SunFounder Arduino UNO R4 Minima Ultimate Sensor Kit. This kit is packed with everything you need to build amazing Arduino IoT projects. So, if you're still looking for a learning kit, I encourage you to please check this one out. This is available on the SunFounder website as well as on Amazon. The links are provided below. So now, let's begin. For this session, you need the following materials: an SG90 micro servo motor, a 10 kilo ohm potentiometer or the SunFounder rotation module, two photoresistors with two 4.7 to 10 kilo ohm resistors, or you can simply use two SunFounder photoresistor modules. And of course, a breadboard, some connecting wires, and your Arduino UNO R4 Minima. In lessons 8, 9, and 10, you've learned how pulse width modulation can be used to control RGB lights and play musical tones with a passive buzzer. In today's lesson, you'll learn how to use a similar technique to control a servo motor. Servo motors are self-contained electric devices that can rotate or position to a specific angle. Using a servo motor is one of the easiest ways to add motion or movement to your electronic projects. Servos are found in many places, from toys to home electronics to cars, robotics, and airplanes. And if you ever played in a remote control car or perhaps a drone, then you definitely use at least a few servos. So, how do servo motors work? Servo motors have three wires, and they follow a specific color code for the power, the ground, and the control signal wires. The power wire is usually red and should be connected to the positive terminal of the power supply, commonly about 4.8 to 6 volts. The ground wire is usually black or brown and should be connected to the ground. And the signal wire is usually yellow, orange, or white and should be connected to a PWM pin of the microcontroller. In this case, I'll connect it to pin 9. Servo motors are controlled by sending a PWM signal to the signal line of the servo. Servo motors generally expect a pulse every 20 milliseconds or 50 Hz, although many RC servos work fine in a range of 40 to 200 Hz. Now, the width of the pulses determines the position of the output shaft. When you send a servo a signal with a pulse width of 1.5 milliseconds, the servo will move to the neutral position, which is 90 degrees. The minimum position is 0 degrees and the maximum position is 180 degrees, typically corresponding to a pulse width of 1 millisecond and 2 milliseconds respectively. But please note that this can vary slightly between different types and brands of servo motors. Many servos only rotate through about 170 degrees, or even only 90 degrees for some, but the middle position is almost always at 1.5 milliseconds. Most RC servos are from the 180-degree variety, which means they can only rotate in a range of 0 to 180 degrees. However, continuous rotation, also known as 360-degree servo motors, is also available. For this demonstration, I am using an SG90 180-degree micro servo motor. The easiest way to control a servo motor is to use the servo library, which comes pre-installed with the Arduino IDE. An Arduino library is a collection of files that provides additional functionality for your sketches. Libraries make it easy for us to work with different hardware components, manipulate data, and perform various tasks without having to write a bunch of code from scratch. Now, the servo library works great in the previous version of the Arduino Uno, the Rev3. However, if for some reason you encounter an error while compiling with this pre-installed version, try updating or installing this library from the library manager. And to do that, simply type servo on the search box and select the servo by Michael Margolis, Arduino, and then install the latest version. You can also click the More Info link to read additional information about this library, like its compatibility, its usage, examples, and available methods or functions that you can use, like this attach, write microseconds, and others. So to start controlling this servo motor, we need to type #include servo.h. The #include is a preprocessor directive that we use to tell our current sketch to include the code from this library into our current program, so that we can use its functionalities in our sketch. After that, we need to create an object of this servo, which I'll call servo1. So the type is servo and the variable name is servo1. To use this servo1 object, first I'll define the servo pin at pin 9. Now, in the setup function, we need to call the attach method and pass the servo pin as an argument. To set the position or the angle of the shaft, we use the write method. This method accepts one parameter, which is the angle from 0 to 180 degrees. So, to test if we can control the servo, I'll position it to 0 degrees, and then a delay of 2 seconds before changing its position to 180 degrees. Another delay of 2 seconds, and finally, set its position to 90 degrees. So, let's upload our program to see if it works. So, that's 0 degrees, and that's 180 degrees, and finally, that's 90 degrees. Aside from the write method, we can also use the write microseconds method. However, using this method requires a pulse width parameter in terms of microseconds instead of the angle in degrees. On standard servos, a parameter value of 1000, which is 1 millisecond pulse width, is equivalent to 0 degrees. A value of 2000 or 2 milliseconds is equivalent to 180 degrees. And a value of 1500 or 1.5 milliseconds will always position the shaft in the middle, in this case 90 degrees. Let's try uploading this code to see if it works. Now, that's 1 millisecond pulse width, and that's 2 milliseconds pulse width, and that's 1.5 millisecond pulse width. As you observe, the angle only ranges from about 45 degrees up to 135 degrees. It does not cover the entire 0 to 180 degrees. The reason is that some manufacturers do not follow this standard very closely. Most servos respond to values between 700 and 2300, representing 0 to 180 degrees. Feel free to increase these endpoints until the servo no longer increases its range. Note, however, that attempting to drive a servo motor past its endpoints, this is often indicated by a growling sound, should be avoided. Now, in this SG90 micro servo motor that I am using, the range is from 500 to 2500 microseconds, or 0.5 to 2.5 millisecond pulse width. So I'll upload the code and see if it works. And now that's 0.5 milliseconds at 0 degrees. That is 2.5 milliseconds at 180 degrees. And finally, that's 1.5 milliseconds is always positioned in the middle at 90 degrees. Now, another important part of the Arduino documentation is the example sketches that come bundled with libraries. To open the example sketches bundled in either the pre-installed or custom libraries, navigate to File, Examples, and find the library you're searching for in the list that appears. Here, we can see 2 example codes for the servo library. I'll open the sweep example. So let's understand how this code works. First, an instance of the servo object is created. It is called myServo. And then, an integer variable pos, initially set to 0, will be used to store the angle or position of the shaft. In the setup function, pin 9 is attached to the servo object. And finally, inside the loop function is where the sweeping happens. It has two for loop statements. This first one loops through the value of the pos variable from 0 to 180, incrementing 1 for each iteration. So inside this for loop, the right method is called to position the angle of the servo, and then calls a delay function for 15 milliseconds before looping back to increment the angle. This 15 milliseconds is the waiting time for the servo to reach each position before setting a new one. So in short, this code will simply position the servo from 0 degrees up to 180 degrees at a speed of 15 milliseconds per degree. And then, after finishing this first for loop, the second for loop is the exact opposite. It goes from 180 degrees down to 0 degrees at a speed of 15 milliseconds per degree. And finally, it loops back and performs the same process again. I'll upload the code and see how it works. And as you can see, it works. However, you might notice that the sweeping motion is a bit jittery, or at least not as smooth as you would expect. Now, I tried using the same code using the built-in servo library on the older Arduino UNO R4, and the sweeping motion is smooth. So, upon checking some of the forums regarding Arduino UNO R4 having issues with the servo motor, I saw this PWMServo at GitHub from Paul Stoffrosen, merge pull request from Kurt E. Now, according to Kurt E., this issue is commonly caused by the servo library having inconsistent pulse width to the servos. So, if you want to test this library on your UNO R4, I provided the link below. Now, all you have to do is to click this code and download zip. And then on your Arduino IDE, go to the sketch menu, include library, and choose add zip library. Browse for the zip file and click open. This should install the PWMServo library. And after that, in our sketch, instead of including the servo.h, I'll include the PWMServo.h. And then, instead of creating a servo object, I'll create a PWMServo object. And that's it. Now, let's try to upload this code and verify if it improves the sweeping motion. And as you can see, the sweeping motion is now smooth as compared to the previous one when we used the servo.h library. We can also control our servo motor using a potentiometer. We can set the servo position based on the knob or shaft position of the potentiometer. To do this, let's hook up a simple potentiometer voltage divider circuit, or we can simply use the potentiometer module from SunFounder. If you want to review how potentiometers work, I've included the video link below. Now in our sketch, I need to define the sensor pin A1. This is where the output pin of our potentiometer module is connected. Inside the setup function, I'll delete these codes since we no longer need this for this demonstration. Instead, what we need is serial communication. Inside the loop function, I'll declare an integer variable val and then store the potentiometer's analog read value. So for the default ADC resolution of 10-bit, we are expecting an analog read value of 0 to 1023. Now, if we're going to use this value of 0 to 1023 to determine the position of the servo motor from 0 to 180 degrees, we need some sort of math computation in our code, like linear interpolation. For example, if our input range is from 0 to 1023 and our output range is from 0 to 180 degrees, and if we have, for example, 512 as our input value, assuming this is the analog read value from our potentiometer, what will be our output value that will determine the position of the servo motor? In this case, that's about 90 degrees. So let's test another input value here, say 256. And as you can see, the computed output value is 45 degrees. Now, in Arduino, you don't need to write a code for this computation. Although you can if you want to. However, there is a function that you can use to convert a value from one range to a different one effortlessly. The map function. The map function also uses a similar technique of linear interpolation. However, it uses integer math, so this function will not generate fractions. This means that fractional remainders are truncated and only returns whole numbers. So, the map function has 5 parameters. The first parameter is the input value to be mapped. In this case, we wanted to map the analog read value. The second and the third parameters represent the lower and upper bounds of the input value range. That's 0 to 1023. While the fourth and the fifth parameters represent the lower and the upper bounds of the output value range. That's 0 to 180 degrees. Now, the return value of this function is the mapped output value. And in this case, the position of our servo motor. So, I'll declare a variable, pos, to hold this value. Now, for us to see both values, the potentiometer and the servo position, I'll print them on the serial monitor. And of course, we need to call the servo write method and pass in the pos value. And finally, a short delay of 15 milliseconds to give the time for the servo to position. Now, let's upload the code and see what happens. And as you can see, it works. We were able to control the servo position based on the potentiometer's knob position. However, you might notice that the potentiometer's rotation is opposite to the servo motor's rotation. The potentiometer's value of 0 to 1023 is in clockwise rotation. However, the servo motor's value of 0 to 180 degrees is in counterclockwise rotation. We can easily resolve this by simply rearranging the parameters we passed to the map function. One way is to swap the fourth and the fifth parameter values so that the lower and the upper bounds are now 180 degrees to 0 degrees. So, let's upload the code and see if it works. And it works perfectly. Now, controlling a servo motor using an LDR or photoresistor is basically the same as using a potentiometer. So, I'll replace this potentiometer module with a photoresistor module. And now, notice that as the LDR receives less light, the servo motor position also decreases. And as the LDR receives more light, the servo motor angle position also increases. Please note that this behavior can be changed. Recall that there are two ways you can implement a voltage divider circuit when using photoresistors. If you want to refresh your memory on this topic, I provided the link in the description below. Now, this topic leads to your challenge activity. For your challenge activity, I want you to modify this program so that it allows the use of two photoresistors. You are going to create a single-axis solar tracker with two photoresistors placed on the opposite ends of the breadboards, simulating east and west location. The servo motor is placed in between the two photoresistors such that when the east photoresistor receives more light as compared to the west photoresistor, the servo motor position will point towards the east. This means that the angle should be less than 90 degrees and below, tilting toward east. You can also verify this to the value being negative. This value is the difference between the east and the west photoresistor analog read values. In this case, east sensor analog read value is greater than west sensor value. On the other hand, as the west sensor receives more light, indicated by this positive value, the servo motor tilts toward west. This means that the angle should be more than 90 degrees and above. In this case, west sensor analog read value is greater than the east sensor. Now, this functionality is easy to accomplish, and the code is very similar to the given example. You just need to identify what range of values you need to pass to the map function. Again, thank you so much for joining me in this lesson on servo motors and building a single-axis solar tracker using photoresistors. For our next lesson, you'll learn how to write non-blocking code using the milis function. If you found this lesson enlightening, don't forget to hit the like button, subscribe for more knowledge-packed sessions, and ring the bell to stay updated. So, keep learning, keep experimenting, and always remember, education is life. See you in our next lesson. Happy coding!